All right, so we're going to be taking a look at the solar nebula theory in Earth's early history, thinking about how material in the solar system supports the age and formation of the Earth. So, our planet was formed during the formation of the solar system, right? The solar system contains the sun and all of the planets, and all of these things that are in the solar system are revolving around the sun, right? That's the main gravitational pull in the center of our solar system. So the solar system contains many different objects, some of which contain the sun, the planets like Earth that we're on right now, moons, comets, asteroids, and meteors. So on the right side of your notes, quick jot down, what's the difference between a planet, a moon, and a comet? So we know what a planet is. We're on one right now. We see a moon up in our sky at night. Sometimes we might even see a streaking comet across the sky. So what is the difference between the three? Take a second to jot that down on the right side of your notes. Okay, so the solar nebula theory. This is one that is the current accepted explanation for how the solar system was formed. When we did our first Explorer, we looked at 5 different theories that were proven wrong, but the solar nebula theory is currently the best hypothesis about how the solar system actually formed. So the solar nebula model states that the sun and planets formed through the collapse of a rotating cloud of interstellar gas and dust. So we are thinking that everything formed from this big sort of disk of stuff that was kind of spinning and had this rotational motion and eventually made its way to what we know our solar system to look like today. So now looking at how specifically the solar system formed. We know that first, the solar system must have started from a nebula, right? That's the first stage of our star life cycle, so we know that that's what had to kick things off. So remember, in the nebula stage, there's lots of gas and dust, and we know that usually this is the birthplace for stars, right? That's kind of how we understand the star life cycle starts. So roughly about 4.6 billion years ago, it is thought that a nearby supernova happened and started to kind of move things around in the nebula that formed our solar system. So this big explosion happened nearby, sending what we say as a shock wave through the nebula to kind of spark motion inside the nebula. And we know when things that are massive get near each other, okay, now the gravitational force has increased, right? Newton's law of gravitation. When things are closer together, there's going to be a higher gravitational force. So things start to move together. Things start to become attracted to each other, and that really starts this whole process. So on the right side of your paper, why is a supernova thought to start this process? Well, if we think back to our stars and elements unit, we know that a supernova is something that sends this big explosion out in many different directions. And we said it releases a ton of energy. And it is through that release of energy that creates this kind of pulse shock wave that starts the collapse of our nearby nebula. So how did we get our star to actually form? Well, going back to star life cycle, we know that when the material started to get pulled together by this increase of gravity, because stuff is colliding into each other, we know that we start to form a protostar, right? That's our second stage of a star life cycle. And we can actually see that in here, that's where our protostar is forming. There's lots of energy, lots of heat, right, where this protostar is forming. But we can also see, wait a second, there's tons of stuff around that protostar, right? It's not just the protostar that's forming and collecting everything. The protostar is at that hot point in the middle, but there's tons of stuff kind of hanging around that protostar as well. So as gravity continues to pull this protostar together, some of those elements and those particles in the protostar start to actually stick together, and that's what we call this process of fusion. And because we have this massive release of energy, this force from fusion that we talked about in our stars and elements unit, this starts to push some of those outer layers away from that forming star. So it's kind of pushing some of that lighter material farther outward. So on the right-hand side, when fusion begins in the star, what stage is it entering? We know that when fusion begins, it is in the main sequence stage. Okay, now I want you to take a second and do this one by yourself. Make a prediction on the right-hand side. What is a similarity and a difference between the accretion of a star and the accretion of a planet? How do you think those things are different? Take a second. Give me a similarity and a difference on the right-hand side. Okay, so talking about accretion. So we know from our first Explorer activity, when gravity pulls together smaller materials and metals and dust and rocks, that process is called accretion, right? It all comes from gravity. So on the right-hand side of your notes, I want you to draw something like this. We have a bunch of small particles, and eventually, when those particles accrete, they become less abundant and also more massive. Or in our case, that when we looked at our play foam in that Explorer activity, we had less spheres after we moved our hand around the paper, and those spheres were larger in diameter. So gradually, when things start to pull together, there is this rotational motion that occurs, and things when they're moving and coming together in space, they're often found to be spinning. So what we find is that the rock and the metal and the gas and the dust and all of the stuff around the sun start to spin around that gravitational point. We can think back to our ENGAGE activity where we had the big sheet in our Kepler's laws unit, and we saw how marbles are moving around the sun. They form this kind of flattened out disk, and we can kind of see that right here. This is our disk around the sun. Now, some of the heavier stuff is going to sink towards the middle. That makes sense, right? Some of the heavier stuff is going to be more attracted to the sun because of Newton's law of gravitation, which means some of our lighter stuff is going to be found in those outermost layers there. So there's still lots of stuff that's around the star. We're just most likely going to see our heavier stuff inside, and then we're going to see our lighter stuff on the outside. So on the right-hand side of your notes, let's see if you can label where those heavy and light materials are, and then where we'd expect to see rocky materials and more gaseous materials, so things made of gas. Go ahead and label that on the right-hand side of your notes. Okay. Now, what do you think? What is the difference between the accretion of a star and the accretion of a planet? What do you think? We made a prediction a couple slides ago. Go ahead and answer this on the right-hand side. Okay, now let's get into our planet formation. There's a couple steps here to planet formation. First step is we get really, really small grains of rock and dust up to 3 feet in diameter, so only a yard, not very big. They start to accumulate into larger bodies called planetesimals. So they start to build up into these larger bodies, up to a half a mile in diameter. This is called planetary accretion. So really, really small bits and pieces start to come together due to gravity. These planetesimals can accumulate into larger bodies called protoplanets. So first step is our planetesimals. Planetesimals is number 1. Then we have protoplanets, which is number 2. And then eventually those protoplanets will grow into full-sized planets. So planetesimals, protoplanets, full-sized planets. Okay, now we said the heavier stuff is going to sink towards the middle, while the lighter stuff is going to be on the outside. Well, we know that certain elements and compounds will condense and solidify during this planetary accretion process, depending on their temperature and mass. So rocks and minerals that have a higher melting point can actually find their way closer to the sun. Again, they're usually heavier, so that tends to make sense. We're going to see those materials from 0.2 to 5 AU away. Remember, the sun is 1 AU away. Sun is 1 astronomical unit. So those heavier materials, those metals and those rocks, are going to be closer to the sun. Whereas those lighter materials, like hydrogen compounds or different ices, like methane is one that we see a lot in our solar system. Those methane and ammonia compounds are only going to be found kind of towards the outside, anything more than 5 astronomical units away. This imaginary boundary, kind of like this melting and boiling point of these different elements and compounds, this is called the frost line. And we can think of it like all the stuff outside of the frost line is going to be, well, frozen, and everything on the inside of the frost line probably isn't going to be frozen, right? It's going to be blasted away or evaporated because it's too hot being that close to the sun. Okay, on the right side of your paper, I want you on this picture below to draw and label where the frost line is. All right, so thinking about the frost line and how this kind of boundary between stuff on the inside and stuff on the outside, we can first talk about our terrestrial planets. So terrestrial planets are the ones that are made up of mostly rock and metal. So like our Earth is right there. Our Earth is a terrestrial planet. So these protoplanets and planetesimals will go through planetary accretion, and since they're mostly made of rocks and metals, these are on the inside of the frost line, then we will form into what we call terrestrial or rocky planets. As you can see up here in this picture, all of our terrestrial planets have metallic cores. So if we think about the core of the Earth, right, there's an outer core and an inner core. So the outer core is liquid, inner core is solid, but they're both made up of mostly iron and nickel. So they are made out of metal. And we know that's true for Mercury, Venus, and Mars as well, that there is a metallic core at the center of all 4 of those planets. Now their crusts and their mantles, if they have them, a separated mantle, are made out of mostly rocky compounds. So like Earth's crust is obviously rocky. If you go outside and dig down, you'll find some rock, and it's very silicate heavy and very magnesium heavy as well. But that is different metals that are found mixed in the rock in the crust of the Earth. So Mercury, Venus, the Earth, and Mars are these 4 terrestrial planets. Those are the rocky planets. Now moving outside of the frost line, we have our Jovian planets, or our gas planets, or in other words, sometimes people call these gas giants. So we have 4 planets outside the frost line called these Jovian planets. Now these are mostly composed of hydrogen compounds, so a lot of ammonia and a lot of methane. Those are hydrogen compounds, as you can see right there. And the reason that we have lots of this ice-type compound is because it's, well, outside the frost line. If they were inside the frost line, all of that ice would melt and be evaporated and kind of blown away. So that's why all of these gases and ices have kind of collected outside of the frost line. So gravity helps capture some of these compounds to make planets like Jupiter, Saturn, Uranus, and Neptune, right? So we know that Jupiter, Saturn, Uranus, and Neptune all have lots of gas, and a lot of them actually have like frozen methane and some kind of frozen surface to them as well. So on the right side of your paper, go back to the solar system picture and give 2 details of the planets inside and outside the frost line. So assuming that you put your frost line in the correct spot right there, this is our frost line, give me 2 characteristics of the terrestrial planets on the inside right over here, and 2 characteristics of our Jovian planets on the outside of the frost line there. Okay, so that covers our 8 planets that we have in the solar system, our terrestrial on the inside of the frost line and our Jovian on the outside of the frost line. But there's one that's close to us, or not a planet, but rather a natural satellite, our moon. And our moon actually has quite an interesting history. So Earth only has 1 moon, as we know, and we can see it in the night sky sometimes in the morning. But the Earth got here from a very interesting path. So the current accepted theory suggests that there was this very old planet that was about the size of Mars that actually collided with the Earth. Now think of this, two planets smashing into each other. Like, this is the type of explosion and eruption we'd think to see if this were to happen, right? Mars just smashing into Earth. So as you can see at this point in the GIF, yes, the outer layers of this planet, this Mars-sized planet that hit Earth, these outer layers actually shatter off, and you can kind of see that happening here on the Earth as well. So we have lots of stuff that just gets flung out into space, right? Bits and pieces of the Earth's crust along with this Mars-sized planet's crust just getting mixed and flung out into space. Now, most of the rocks from Earth's outer crust would have been literally obliterated and sent out into Earth's orbit from this incredible impact that happened. Oops, sorry, I got to go back here for a sec. So we have our Earth in the center, and then all this stuff gets kind of blasted out into space. Well, when stuff is in space and it's near another massive body, well, okay, gravity's going to take over and kind of keep it around. Well, this starts to form something similar to what we talked about earlier, some sort of like accretion disk in there. And then what happens is that this stuff starts to come together through the process of accretion. Okay, just run it back one more time. And now, instead of forming a planet, because there's only bits and pieces of the old Earth's crust and the old Mars-sized object's crust, we have this smaller rocky thing that's actually going to orbit around the Earth, and, well, we know that rocky thing to be our moon. So it actually forms this almost like Saturn-like ring around Earth, but then gravity starts to take over. We start to see these small amounts of accretion happening, and eventually, fast forward a couple, hundreds of millions or billions of years, and we get an Earth with the moon revolving around it. So we actually see this accretion aspect yet again. So we have the combination of these bits and pieces of crust, and it forms into what we know as the moon today. Okay, and then our last topic is this sort of cataclysmic event, or this time period of Earth called heavy bombardment. So the very final stage in Earth's formation is called the heavy bombardment period. So this is a time that, for whatever reason, like, we don't have a great understanding of why this happened. We have some ideas. There's lots of bits and pieces and debris moving about in the solar system at this time. But this is a period of increased meteorite impacts on planets and moons, especially with our terrestrial planets inside the frost line. Evidence of this time period can be found by looking at craters. Well, where do we see lots of craters? Well, looking at the moon. Like, we can literally see with the naked eye craters on the moon. This is one of the theorized ways that water was actually brought to Earth. So not too long ago, a couple billions of years, Earth wasn't a super hospitable place. Like, this wasn't a great place to live. Our atmosphere wasn't made out of a ton of oxygen. There wasn't a lot of liquid water. So some scientists theorize that this period of heavy bombardment, of literally just getting pelted over and over again with meteorites, is actually one of the ways that some of these things that contain ice flung into the Earth and deposited some of that water on Earth. So this is a period that is hotly debated in the scientific community, but we can actually see evidence of this time period by just straight up looking at the moon. So we know that the moon had to form first because there's evidence of craters on the moon, as you can see kind of in the sky here. But this would be our last stage of our planet formation. Now, last thing I want to leave you with today, and this is going to wrap up our notes. On the right side of your paper, why do we see a bunch of craters on the moon, but we don't see many craters, if any at all, from this time period on Earth? Why is that the case? This is kind of wrapping back to our engage activity. Why is that the case? What do you think? Answer that question on the right-hand side, and that's going to wrap our notes for today.